Today we will discuss transistor sizing for near threshold voltage operation for combinational circuits. So, we will first discuss transistor sizing and its impact on combinational circuit operation in near threshold voltage. Then we will go more in detail of WP by WN ratio of CMOS inverter and logical effort of CMOS inverter, and also gates with stacked transistors, how their logical efforts can be estimated. So, the most basic combinational static combinational gate is CMOS inverter. So, in this let us see what is the difference in the operation of CMOS inverter in above threshold or super threshold regime and in near threshold regime. So, when the output voltage increases, VDS of the N MOSFET increases. So, this direction VDS of N MOS increases, and when output voltage reduces, it is the VSD of P MOSFET which reduces. Okay. And with the change in the input voltage, the change in current, because you are operating in near threshold or sub threshold regime, the change in current is exponential. This is a log scale, y axis, x axis is a linear scale. So, what we see is, and what are the points where your input and output voltages can have a value in static characteristics? So, it is these where the currents match, the PMOS current and the NMOS current. So, where these two match, that is where the static characteristics can, the points which exist on the static character. So, what do we mean by this? So, these are the currents of N MOSFET and these are the current curves of P MOSFET. So, wherever they meet, that is the value of current which can be commonly flowing from the P MOSFET to N MOSFET. What do we mean? So, for that value of input, for example, this value of the input voltage, which is a certain value 1. So, certain value for input voltage VGS, VGS is increasing in this direction, VGS of N MOSFET, okay, and VSG of P MOSFET is reducing thereby as you go above like this. So, these are for different values of VGS of N MOSFET and different values of VSG of P MOSFET. So, here what would be happening? This is the current which can flow from P MOSFET to N MOSFET. So, at this value of output voltage and this value of VGS of P MOSFET and VSG of N MOSFET, that is a certain V in, VGS of N MOSFET and V in. So, this is, if we observe, this voltage difference is VSG of P MOSFET and this is VGS of N MOSFET. VSG of P MOSFET is VDD minus V in. VSD of P MOSFET is VDD minus V out, okay, and VDS of N MOSFET is V out. V in, VGS of N MOSFET is V in, okay. So, what we observe is that for little change in V in, there is a huge change in the current, okay. So, there is a large change in the current of N MOSFET, okay, and a large change in the current of P MOSFET as well. So, the N MOSFET current increases and P MOSFET current reduces by a very large value. So, that is why what we would observe is that in this part of the regime where the currents are saturated, for a small change in VGS of the N MOSFET, the matching of currents would happen. So, now there is a small change in the current of the VGS of the N MOSFET in this regime. Suppose here, and then there is this change, okay, small change in V in, but that would result in a very large change in V out. It would result in a very large change in V out. So, but what would happen in super threshold regime? This change in current is not so large, it is a linear scale, it is not on log scale, it is not exponential with VGS. So, therefore, since the change in current is not so large, for a small change in VGS, you would not have this in when both the currents are saturated. See here the N MOSFET and P MOSFET, both the characteristics are in saturation. So, even here in super threshold regime, for a small change in input voltage, you will find a large change in output voltage, but it would not be such large because the change in current with VGS is linear or square law, it is not an exponential change. So, if you want to look at it as an amplifier, the amplifier gain is very large here. Why? Because for a little change in input voltage, there is a huge change in output current, and therefore for output voltage also. So, what you find is that for a small increase in the input voltage, there is a large change in the output characteristic. So, in nominal voltage, if therefore the transition or the gain has a significant value, but in near threshold voltage it is much larger, it is much steeper. So, for a small change in, for example, if you increase the input voltage in this saturation regime a little, you would find an exponential increase in the current of N MOSFET. Now, the VSG of P MOSFET is reduced. So, since it has reduced, to increase the current to the same value, you must increase the VDS by a very large value, VSD by a very large value for the P MOSFET. So, that through DIBL or short channel effects, the current matches that of the N MOSFET. So, for that to happen, you would have to reduce V out by a large value. That is what is happening. So, what is this? This region is near threshold or sub threshold saturation. It is not the saturation that we encounter in super threshold regime. Now, let us also see what is the value of V out. For example, if V in is 0, V out should ideally be VDD, but it is not VDD, because in the ion by Ioff ratio is not that large in near threshold or sub threshold regime as in the super threshold regime. So, we will discuss reason for that. Since the ion by Ioff ratio is not that large, so Ioff, for example, if input is VDD, P MOSFET is off, but the Ioff of this is not very small. Suppose in super threshold regime, if the ion by Ioff ratio is say 10 to the power 5, here it would be somewhere around 10 to the power 3 10 or so. So, if it is so, then what happens if this transistor is on and this is off, you should ideally have a VDD 0 here, but since the leakage current through P MOSFET cannot be neglected, you will find that there is little, the voltage here is slightly above 0. Okay. So, because of the leakage current, output voltage would never reach 0 or VDD. Because of the N MOSFET leakage current, when the input is 0, the output would not be exactly VDD, but it will be slightly lesser than VDD. Okay. So, that is one reason that the output voltage is slightly smaller than VDD, but there is also another difference here, that there is this coupling capacitance, okay, which is CGD of both the devices. Now, when the output voltage is falling, because of the coupling capacitance, you would observe that the input voltage also is not rising, and it remains at a relatively lower value, slightly smaller than VDD, or its final value. Final value is not VDD, it is again smaller than VDD, but it would remain at a even relatively smaller value for during the output transition. And these are kinds of effects which are more prominent in near threshold or sub threshold regime, though all of these effects are there in about super threshold regime, but these are all more prominent and important in near threshold or sub threshold regime. So, what do we mean by these static characteristics here? So, it is that for a given value of input voltage, the output would settle to a certain value, and the output capacitance would no longer be either charged or discharged. Suppose the output voltage is larger than what it is supposed to be, then you would have a net current through the N MOSFET that would discharge, but that increases the VSD of the P MOSFET. That increases for you keep input voltage at a certain value, output voltage is suppose larger than what it is supposed to be, then that would result in a net current in the current in the N MOSFET, which is larger than the current in the P MOSFET. So, now that would discharge the output capacitance, but that this would increase the VSD of P MOSFET and reduce VDS of the N MOSFET. So, N MOSFET current keeps reducing, P MOSFET current keeps increasing, they would again match each other, and once they match each other, the output capacitance is neither charged or discharged. So, that is the value at which the output voltage would finally settle down. So, that is the input voltage and output voltage value that you find on the static transfer characteristic. Now, let us discuss the ion by Ioff ratio and its implication. So, what happens when the ion by Ioff ratio changes? So, one way to reduce ion by Ioff ratio is by reducing VDD. So, let us discuss that. Suppose V in is VDD and now you reduce VDD. V in is also VDD, you reduce overall VDD. Okay. this is 0, still this is 0, it does not change the output voltage value. So, if this is, so what happens to the VSD of the PMOSFET? So, that reduces. So, since VSD of PMOSFET reduces because of DIBL, you would find that the PMOSFET leakage current reduces or off current reduces, is not it? Okay. So, what about NMOSFET? NMOSFET V in is VDD. So, since the PMOSFET leakage current reduces, and what happens to the NMOSFET current? Now, what is the value of NMOSFET VGS? That is again VDD. So, it has also reduced. So, since NMOSFET VGS has reduced, the and its VDS, what has happened to its VDS? So, its VDS is, so this is VDD and this is 0. Okay. So, its VDS remains almost the same. So, because of the DIBL, this has an relationship like lambda VSD divided by NVT, the current, and IN is proportional to exponential V in by NVT, VDD minus V out. So, we are looking at the case where V out is 0. So, the PMOSFET, it's you are not reducing its terminal voltage VSD is reducing, and its VSG is also reducing in magnitude. And the NMOSFET, it is supposed to pull the output voltage to 0. So, its current is also reducing because its input voltage, its gate voltage is reducing. Okay. So, as you keep on reducing VDD, you will find that the current, leakage current, okay, suppose you plot this. So, this is the, suppose you are operating at this value of VDD and then you operate at this value of VDD. So, you have reduced VDD. So, your on current reduces exponentially, whereas the leakage current remains the same for the same technology. So, what is happening is here you are keeping the same leakage current. So, the on current is reducing and the leakage current is almost remaining the same. So, relatively I on, so from VDD 1 to VDD 2, I on by I off reduces. Okay. So, what is the implication of this? We had seen that this difference is because the off current of the PMOSFET gives rise to a certain VDS of the NMOSFET, because VDS of NMOSFET has to rise to fight the off current of PMOSFET. So, now you are saying that when you are reducing it from VDD 1 to VDD 2, the off current of PMOSFET increases further, and therefore, you would find that this difference is even more larger. Okay. So, likewise, this is an exaggerated figure, but you would find that the highest value of the logic 1 and lower the logic 0 value, these two get compromised if ion by Ioff ratio reduces. If ion by Ioff ratio reduces, this difference gets increased. So, you can say that this increases if I of P increases and I on N decreases. So, and likewise this increases if I of P and I on P decreases. So, then this increases, is not it? So, what you find is that if ion by Ioff ratio is compromised, then you find that the static transfer characteristics become more compromised, or they look more, the inverter like characteristic is not well produced. What is the minimum voltage that you want to have? Now, so as you keep on reducing this will, if you keep on reducing ion by Ioff ratio further or VDD further, you will find that this becomes like this. So, finally, you would find that the logic values are quite compromised, and this transition also grows. That is because your currents are comparable in both the modes, off and on. So, ultimately what would happen is that theoretically, ultimately the minimum voltage found by Meindl and others is such that the characteristic becomes never has a value of -1 slopes. So, this is a -1 slope and this is again a -1 slope that we see. So, you would never have a -1 slope in the transfer characteristic and that is where you say that this is the minimum voltage. Why -1 slope is so important? Because here the gain is lesser than -1 and here the gain is greater than -1 in magnitude. So, what you mean to say is that for any noise in the input is not amplified in these regions and any noise in the input is amplified in this region. So, there is a change of state here if there is a noise in the input there can be a change of state. Okay. So, here we have discussed ion by Ioff ratio and its implication on circuit behavior. This we had briefly discussed previously. So, as you decrease the subthreshold swing, so this is the subthreshold swing. So, a larger, so this is a, so if you have this value of subthreshold swing, you would say that S2, this is suppose S2 and this is suppose S1, then S2 is smaller than S1, okay, because you measure it as millivolts per decade of current, millivolts per decade of current, okay. So, that is why S2 is smaller than S1. So, if S decreases, then ion by Ioff ratio increases for near threshold, because for these two values of VDD, here we would have had this current and this. So, if S decreases, you would find that ion by Ioff ratio reduces. Okay. If S is large, then for the same change in gate voltage, you would find a smaller change in the current I, and for a, if S is small, you would find a larger change in current I for the same change in gate voltage. So, Ioff is the same for both the scenarios. If Ioff is the same and subthreshold swing changes, what happens? The Ioff is the same, but if you reduce the value of S, which is a good thing, you would find that, so if you reduce the value of S, for the same value of VDD, ion the current value increases and Ioff is the same in this case scenario. So, ion by Ioff is better, but what happens to delay? So, from here, so here this is suppose S3, S3 is suppose this is, so now you have reduced the value of subthreshold swing in S3 from this value, you have reduced the value of subthreshold swing. So, but you have also changed the value of Ioff. Okay. So, what happens in this case? In this case, for the same VDD, though ion by Ioff ratio has improved again, the ion by Ioff ratio has again improved in this case of decrease in S also, but you would find that the current has reduced, current has also reduced, the current at VDD1 ion has also reduced. Therefore, delays would increase in this scenario, delays would increase, that is you reduce the subthreshold swing by reducing the off current. In that case, the delays would increase, because for the same VDD you would observe that there is a smaller current. Okay. Now, let us suppose we have series stacked transistors, that is an AND gate. So, in this for a given value, so suppose one of the inputs is off, suppose this is VDD and this is 0, then output should be VDD ideally. And what about Vx? Vx would have a certain value which is larger than, so this will Vx would have a value which is larger than 0 and Vx would also be smaller than VDD. So, VGS of A, transistor A, would be VDD minus Vx. So, it would be a smaller value. So, suppose this is the value of VDD that we are discussing. Now, Vx would be having a VGS, transistor A would be having a VGS which is smaller than this VDD, transistor B would have a VGS which is 0, transistor A would have a VGS which is VA minus Vx, and that is smaller than VDD. Okay. So, for VDD this is the current, for a smaller value, this is the current which is exponentially reduced current. So, the current changes exponentially with VGS. So, since its VGS is smaller, it would be exponentially smaller. Now, if S is smaller, if S is also smaller, then the current through this transistor A would be even smaller, because for smaller S, the change in current is larger from VDD 1 to VDD 2. Likewise, from VDD to VDD minus Vx, the change in current would be larger for smaller s. If s is reduced, Ia is further reduced, okay, because of this reason. So, what do we mean to say that if s is smaller, then the leakage current through a series stack is smaller, okay. So, now in the previous lectures we had discussed of effective W. So, that means if S is small, effective W, which is in terms of the inverter leakage, the effective W also is smaller, and that would, if, and we had seen in the previous lecture that if effective W is made smaller, for then optimum VDD, minimum energy point, also moves down. So, VDD optimum also reduces because of this. So, we discussed implications of subthreshold swing S if it is varied. Suppose in this you keep on reducing the value of WP, what would happen? So, in state VDD, if an input is VDD, if you reduce WP and keep Wn constant, then if V in is VDD, V out would finally reach near 0, okay. But if V in is 0 and V out is supposed to be VDD, but WP is smaller. So, IP of this WP which is reducing would also reduce, whereas since Wn is the same, In is constant. So, what would happen? Therefore, you, since IP has reduced, you need to maintain a smaller VDS to match the reduced IP. V out reduces. So, V out's value, if it was a small value above the ground, it would become even more smaller if WP reduces, okay. So, that is what we are seeing here. So, when WP reduces, you would find that for V in being 0, you reach a value, highest value, which is, you would find that for V in is equal to 0, V output high also reduces, because In is almost the same or constant, IP reduces. So, therefore, for a reducing WP, you would find that VOH reduces. So, now VOH, if we want VOH to be larger than or equal to 90% of VDD, suppose. So, in that case, you would have an upper bound on the a lower bound, you would have a lower bound on WP for a given VDD. Suppose you reduce the value of VDD. If you reduce the value of VDD, what happens to the, so from our previous discussion, if you reduce the value of VDD, this lower bound, so this VOH would become even smaller, because the current through P MOSFET should now match for a reduced value of VDD, the VSG of P MOSFET is now smaller. So, therefore, the current through P MOSFET now again should match the leakage current of N MOSFET. So, V out will rise. So, V out will fall, V out will fall, because the current through N MOSFET is the leakage current, it is the same, whereas the current through P MOSFET is reducing. So, value of V out would fall further, but to bring it back to be larger than 90% VDD, you need to increase WP, okay. So, like therefore, WP is increasing here as you reduce VDD. What about the other bound? So, here you are keeping Wn constant. So, now the other bound is that output voltage should be larger than a certain value for V in being VDD. So, when V in is VDD, you can argue just these arguments, are a dual of these arguments have to be put forth. So, when V in is VDD and So, you keep on increasing the value of when V in is VDD and you keep on increasing the value of WP, leakage current through P MOSFET increases, and that has to be countered by the current through N MOSFET. So, now for that V out should increase, increasing the VDS of N MOSFET. Okay. So, V out is now larger than 0, it becomes even larger when you increase WP. So, you want V out, suppose V out to be within 10% of VDD, then you have an upper bound on the size of WP, there is an upper bound. If you reduce VDD, what happens to this upper bound? So, when you reduce VDD, the current through, so now input is now VDD for the N MOSFET and its VDS is almost 0. Okay. So, the current through P MOSFET also reduces because its VSG is reducing, and that would keep an, so therefore, this upper bound on WP also keeps on reducing. So, wherever these two meet, so you keep on reducing this. So, here beyond this it is not physically possible. So, here the upper bound on the P MOSFET size and the lower bound on the P MOSFET size both are matching. So, what do you mean? So, you mean to say that beyond this, if you reduce VDD any further, you cannot maintain that. Suppose you have kept a bound 10%, the output should be larger than, smaller than 10% of VDD and the VOL, and VOH should be larger than 90% of VDD. You cannot maintain that bound when you keep a VDD which is smaller than this. So, this point gives the minimum VDD, and you should also analyze it for FS and SF corners. So, lower bound of on P MOSFET size should be seen for FS corner, because you want the for lower bound you also want the P MOSFET to be slow, because it should be carrying smallest possible current. Likewise, for upper bound on VDD, you should look at the upper bound on P MOSFET size, you should look at the SF corner, because then the current carrying capacity of P MOSFET is the largest. So, here we have discussed WP by WN ratio based on upper and lower bound on of V out. Okay. One observation, suppose there is no limit on the frequency. So, if the frequency can be very small, it can be compromised, or time period can be very large, this can happen in say sensor edge applications. So, there you are not concerned with speed of operation. So, in such cases you can keep minimum sized transistors. The argument is that if you keep on reducing the sizes of all the transistors, W effective reduces, but almost proportionally C effective reduces. So, VDD optimum remains almost constant. So, if VDD optimum remains almost constant, you would find that the dynamic energy keeps on reducing, because your VDD optimum is not changing, the optimum supply voltage is remaining the same. So, you are not changing, you are changing dynamic, you are reducing dynamic power in proportional to C effective. So, you are keeping minimum size, that is the minimum size transistors, that is the smallest possible C effective. So, you are having smallest possible dynamic power, and because you have reduced the size, the W effective is also reduced. So, leakage power is also reduced, both are at their smallest value, possible value. So, that is why several people argue that using minimum size transistors is the best way for subthreshold design. It is true, if it can be true, if you use minimum, if you have no limits on the frequency of operation. So, if frequency of operation can be extremely slow, then it can be advisable to keep all the sizes transistors at minimum size. If one has to anyway, nevertheless one has to check timing closure and accordingly do this. So, here we have discussed if the circuits are extremely slow circuits. So, let us have a brief discussion on variability. So, there is process variability in all the technologies. So, what is the reason of process variability? So, now there are random changes in doping density, and for extremely scaled technologies you would find that the dopant ions are so few that a small change in doping density would actually result in a large effective change in doping density within the channel. There is line edge roughness, and so there can be several such reasons for variability. Now, what is done is, for a transistor, ion is plotted over a large number of samples, and the mean, it follows a Gaussian profile, suppose. So, in that case you will find out the, say, 3 sigma or 2 sigma values and call this as the fast corner because it has a larger ion, and this has slow corner because this has a smaller ion, and this has typical corner. Now, this would be happening for P MOSFET as well as N MOSFET. So, if it is typical N MOSFET and typical P MOSFET, it could be typical N MOSFET and slow P MOSFET, it could be fast N MOSFET, slow P MOSFET, slow N MOSFET, fast P MOSFET. Likewise, you can have several combinations of these. So, this is the way. So, these are all called corners, process corners, and this is the way where, so variability is characterized in the sense that you would check for the circuit's operation, proper operation at all the corners. So, today we have discussed the implications of ion by Ioff ratio, and also discussed process corners. So, in the coming lecture we will discuss transistor sizing for matching the output fall and rise transitions, and also for estimating logical effort, which would be used in designing combinational circuits.